It's been called the most beautiful equation in mathematics. E to the I pi plus 1 equals 0. But what does it even mean? The exponent, well, that's the square root of minus 1 multiplied by the area, or half the circumference of a unit circle. But what is E? And what does it even mean to raise it to the power of an imaginary number? That's what I'll discuss here. Welcome to Almost Sure. Now it's the time of year again to remember and visit old friends. And an old friend of mine, and many others I'm sure, is the exponential function. Now if you ask a non-mathematician, what does it mean to raise a number a to the power of another number n, then they might be able to tell you that it's just multiplying together n copies of a. But what about non-integer exponents? We can write e to the power of pi, for example, but what does it mean to multiply 3 and a bit copies of e? And then Euler's identity has e to the power of I pi. You can't multiply e, whatever that is, by itself an imaginary number of times. At this point, a mathematician might step in and helpfully explain that e to the x is given by its power series, or some other definition, which if you aren't already familiar with it, then it can just make it seem more confusing. Now, if you know some maths, then I'm sure you're already familiar with exponentiation, in which case you're already familiar with the content of this video. But it's good every now and then to take things back to basics, strip out all the superfluous stuff, and really think about the meaning of concepts that we use every day. Maybe we'll gain some new understanding, or at least some new appreciation of familiar ideas. Let's start simple. Very simple. What is a base number a raised to the power of a positive integer n? Well, that's easy. Just multiply together n copies of a. Anyone can tell you that. But we can do a little better mathematically. Saying multiplying together n copies is a bit cumbersome. Stripping back everything to its real basic elements, what even are positive integers? Okay, they're counting numbers. You start at 1 and you count 2, 3, 4, so on, incrementing by 1 at each step. And the exponential can be defined in a similar way, using this basic inductive construction. So a to the power of 1 is just a, then for each x, a to the power of x plus 1 is a to the power of x multiplied by a. As we count through the natural numbers in the exponent, we just keep multiplying by a, giving all the powers of a. For example, a to the power of 3, that's a to the power of 2 multiplied by a, which is a multiplied by a multiplied by a. Let's use this as our starting definition for natural number powers, and we'll keep track of the definition up here. Now, some of you might be screaming at me right now, 0 is a natural number. It's always a controversial subject.
Well, a little over half of people think, yes, they do include 0. A little under half think, no, they don't include 0.
Anyway, let's extend the range to include 0. Our induction step started at 1 though, but never mind. We can still see what the definition tells us, and that is that a to the power of 0 times a is equal to a. And cancelling a gives a to the power of 0 equals 1. At least it does if a is non-zero. So let's start our induction at 0. Okay, hang on. Let's look at that again. If a is 0, then I'm saying that 0 to the power of 0 is 1. Okay, more controversy.
A little under half say the number is 1, but then there's also big groups, about a quarter say indeterminate, and about a quarter say undefined.
And 2.9% of you think it's 0? What? Okay, never mind. We're going to restrict to non-zero bases soon anyway. And applying our current definition up here, we still see that a to the power of 1 equals a, so it agrees with our previous definition for positive integers. But now a to the power of 1 equals a is a theorem. That means it's a property which follows from the definition. And let's keep track of our main properties up here. Now there's plenty of properties of exponentials, which no doubt you're already very familiar with, such as a to the power of x plus y equals a to the power of x times a to the power of y. But let's quickly prove these using our simple definition. And the idea is that if we have a sequence, s of 0, s of 1, s of 2, so on, which multiplies by a at each step, then the s of n term must equal s of 0 times a to the power of n. And this follows directly from the definition. And it must be the unique solution for any starting value s of 0 by induction. So take the example where our sequence s of y is equal to a to the power of x plus y. So we're fixing x here and considering y running through 0, 1, 2, so on. And this sequence multiplies by a every time y is increased by 1. And the first term of the sequence is a to the power of x. So the term s of y equals a to the power of x times a to the power of y by what we just saw. And that proves our identity. Another identity, a to the power of x to the power of y equals a to the power of x times y. We can do a similar thing, but this time we look at the sequence s of y is equal to a to the power of x times y. Now this sequence, again, it starts from 1 when y equals 0. And every time that y is increased by 1, it multiplies by a to the power of x. So by what we just said, the term s of y in our sequence must equal a to the power of x to the power of y. That proves that identity. Yet another identity, a times b to the power of x is equal to a to the power of x times b to the power of x. We do a similar thing, but this time let's look at the sequence s of x is equal to a to the power of x times b to the power of x. So now our sequence has x going from 0, 1, 2, so on. And this multiplies by ab whenever x is increased by 1. And it starts from 1, so s of x is equal to ab raised to the power of x, and we're done. Now let's extend our definition to all integer exponents. That is, we're going to include negative numbers in the exponent as well as positive. We can just try taking the same definition, but we'll just replace the natural numbers n by the integers z or z. There's one issue here though. Let's just check the induction step where the exponent x is equal to minus 1. Now this gives a to the power of minus 1 times a is equal to 1, which is what we expect, that a to the minus 1 is 1 over a, but this can't apply if a is 0. Anything being multiplied by 0 just gives 0 back, not 1. So we have to exclude a equals 0 from the definition. Having done that, let's apply the induction step again, but I'll make a substitution. Let's replace x by minus x plus 1. And doing a little rearranging, we see that 1 over a to the power of minus x. This satisfies exactly the same induction formula as a to the power of x. So it must equal a to the power of x, which means two things. Firstly, our definition uniquely determines all the negative exponents just by taking the induction step backwards. And we also have a new property, that a to the power of minus x equals 1 over a to the power of x. So we can add this to our list. And all the other properties that we have here, they also hold with negative exponents. And you can use the same proof that we did for the positive exponents, where we had this sequence which multiplied by a at each step, except we also take sequences which go in the negative direction. But it's the same basic proof. So let's take a look at what we've got so far. For a base a, the powers look like this. The height scales by a for every step to the right and divides by a for each step to the left. And they do seem to form a nice curve for all values of a that we try. And we could easily fit a smooth curve through them, but obviously there's lots of ways that we could interpolate these points. So how should we do this? Unfortunately, our induction step, a to the power of x plus 1, is equal to a to the power of x times a. That's just not good enough to fill in the gaps. It only relates exponents which differ by integer amounts. So it can't imply the values for non-integer values. So we need to work a bit harder here to make sense of non-integer exponents. Although the definition we're using is not good enough to extend to non-integer exponents, it's possible to step into the gaps between integers using this property here. Take a to the power of a rational number, m over n, and then raise this to the power of n, and our property says that it equals a to the power of m. So the exponential is the nth root of a to the power of m. We've extended to rational powers. Okay, hang on a moment. Before we get too excited, a complex number, this has multiple nth roots. It's got n of them, in fact. So taking complex numbers to the power of rational exponents, this does not have a unique definition. We can try fixing this by just taking the positive real roots, which are unique. But this only works if we suppose that a and a to the power of x are positive real numbers. So let's do that and make that assumption. In fact, it's enough to enforce that a to the power of x is real, then as it's equal to a to the power of x over 2 squared, it's automatically the square of a real number, so positive. And let's add this property here to our definition. And I replace y by n here just because we only need integer values. I'm using n for integer. Now, we have all rational exponents, and all of the properties up here, they still hold, and you can check this, if you like, by raising to large integer powers and reducing them to the case of integer exponents, which we've already proved. So let's look again at our plot of the powers of a, and fill in the exponents at a bunch of rational exponents. It very clearly seems to be converging on a smooth curve. So we should be able to fill in the gaps now. But let's not go so fast. Our definition is getting a bit messy, so let's tidy it up. Starting with this property, a to the power of x plus y equals a to the power of x times a to the power of y. Now that's a pretty basic property, and by repeated applications of this property, it does in fact show that a to the power of x to the power of n equals a to the power of x times n, just like so. So let's use this as our defining property instead. And not only that, but this also almost proves the induction step. In fact, it does prove it if we also know that a to the power of 1 is equal to a. So let's move this property, a to the power of 1 equals a, into our definition, which replaces the induction step. But now we can also show that a to the power of 0 times a is equal to a to the power of 1, which equals a. So cancelling our a gives a to the power of 0 equals 1. So in fact we can prove this property, that a to the power of 0 equals 1, from the other definition. So we don't need it as part of the definition. So let's move it to our properties. And this gives us a very satisfying definition now. It's pretty simple. We have a to the power of x plus y is a to the power of x multiplied by a to the power of y. So exponentiation converts addition to multiplication. let's bring up our plot again of a to the power of x and a set of rational exponents. The property that a to the power of x plus y equals a to the power of x times a to the power of y. This can be understood as a simple scaling property of the graph. Shifting to the right by y and then scaling up by a to the power of y gives the same plot again. Pretty nice. And our only other requirement in the definition is that a to the power of 1 equals a, which we need because it's just defining what the base is. Looking at our plot of a to the power of x again for rational exponents, yeah, it certainly looks like it lies on a continuous curve, and we can show that it does, and then give a unique extension to real exponents. But let's do one better than this. In fact, the curve is convex. That is, the line joining any 2 points on the curve lies above the curve segment between those 2 points, like so. But how can we prove this, that any intermediate point on the curve lies below the line segment? Well, here's one way. Let's subdivide our interval into equal steps. And as everything is rational, we can make sure that one of the intermediate points, equally spaced points, lies on our point that we need. Now look at the gradients of the lines joining these points. Certainly it looks like they're increasing in the plot, but let's write this down. The difference of successive gradients for some spacing h. We can just rearrange this, extract out some common terms of a to the power of x over h, and the remaining terms, let's rearrange them a little bit, and we see that it's a square, so it's non-negative. The difference of successive gradients is non-negative, so they're increasing, as suggested in the plot. Now this means that the gradient joining the left point of the interval to our intermediate point, that must be less than the gradient joining our intermediate point to the right of the interval. And this is equivalent to our point being below the line joining the endpoints, so it's convex. Okay, great, but so what? Well, convex functions, they have lots of nice properties, but one of those nice properties is that they're continuous. In fact, on any bounded interval, they're uniformly continuous. We can do even better than this. The gradient bounding any 2 points inside the interval, well, this must be greater than the gradient to the left of the interval and less than the gradient to the right. So it has got bounded gradient. And this is called Lipschitz continuity. And yes, it's enough to show that they lie on a continuous curve. So all we have to do is take the limit of rational exponents as they tend to any real exponent. So let's add continuity to our definition. And hurrah, we've defined exponentiation for all real exponents. Now, as an aside, not really important to the main thread of this video, but something which maybe boggles the mind a bit, let's look at our definition for the a to the power of x, for real x. We had to assume continuity, so that allowed us to take limits for rational exponents to extend to the irrational exponents. But could we just drop this? Are there any solutions to the identity a to the x plus y equals a to the x times a to the y, which are not continuous? Well, yes and no. Right. Most people would say, yes, there do exist such cases where they're not continuous. But they require the axiom of choice to construct, uncountable choice, where in order to construct this example, we need to make uncountably many arbitrary choices. And this can never be done explicitly, it's just theoretically such examples exist. But not everybody accepts the axiom of choice. In fact, let's welcome back the friend of this channel now.
An axiom that most mathematicians tend to accept. As you can see here, it's about 85%.
Now, I've got good news for those of you who reject the axiom of choice but accept the axiom of countable choice or dependent choice. There are, in fact, models of set theory which reject the axiom of choice but allow dependent choice, and every subset of the real number line is measurable, and in such models, then any function satisfying a to the x plus y equals a to the x times a to the y is continuous. So if you're going to adopt such axioms, such models of set theory as your foundation for maths, then you don't even need continuity here. But we'll keep it in case you want to use the axiom of choice. But what about this special number e? It's known variously as Euler's number, the base of the natural logarithms, or Napier's constant, or simply e. What's so important about this? Well, it does appear all over the place in maths, so there's many things that I could talk about, but here's one remarkable thing. I just mentioned it's known as Napier's constant. But the number e, well, it was first discovered by Bernoulli. In fact, by Jacob Bernoulli. But he wasn't even born until nearly 38 years after Napier died. So what did Napier have to do with this number, which was never discovered while he was alive? Well, it's interesting. Suppose we want to add two decimal numbers together, say 3.141592 plus 4.669201. Okay, easy. All we do is we just add each digit in turn, remembering to carry the ones. But what about multiplying them? Okay, now it starts to get messy. We can use long multiplication, but this is getting slow, it's getting messy, especially when we're doing everything by hand, which obviously they would be doing in Napier's time. Fortunately, logarithms come to the rescue. The logarithm base a, well, this is the inverse function to exponentiation with base a. So y is log of x if x equals a to the power of y. So in particular, our plot of the logarithm, well, it's just the same as the exponential, but flipped to exchange the x and y axes. Now let's look at the product of two numbers x and y. We can write each number as a to the power of its logarithm. Now let's use the fact that a to the power of x plus y is a to the power of x times a to the power of y to combine these exponentials to get this very useful result. X times y is a to the power of log of x plus the log of y. So we've reduced multiplication to addition. Well, we've reduced it as long as we know how to perform the logarithm and its inverse, the exponentiation. And that's what John Napier did. He compiled tables of logarithms in order to quickly do multiplications by hand. Not that it was quick for Napier to construct these tables. In fact, it took him about 20 years, including developing the theory and performing literally millions of calculations by hand. But once compiled, they were amazingly useful for practitioners. Would Kepler have even come up with his laws of planetary motion if he had to spend all his time doing laborious multiplications by hand the long way? Well, maybe not. Anyway, Napier's logarithms, they were to base e, effectively. But e was not even discovered yet. To demonstrate natural logarithms, I have a slide rule. These things were very useful computation devices up until when electronic calculators were invented. So suppose I want to add two numbers, 6.5 plus 5.5. Now, adding two ordinary rulers together, I would line up the 0 on one with the 6.5 on the other, and then I'd look at the 5.5 on the first one and see that it corresponds to 12, which is 6.5 plus 5.5. Now, that's not surprising, right? We just added together the two lengths. But do the same thing with the slide rule. We line up the 1 with 6.5, and then we look to see the 5.5 corresponds to something between 35 and 36. So very close to the exact product of 35.75. And this works because the numbers are not equally spaced. Right? They are logarithmically spaced. So we're actually adding the logarithm of 6.5 to the logarithm of 5.5, giving the logarithm of 35.75. But let's try creating our own slide rule right here in this video. To do this, start with a blank ruler and pick a base A, which I'll take equal to 2. And put equally spaced marks at the top, and at the bottom we put the corresponding powers of A. Now I've taken enough powers of A that we get up to at least 100 at the bottom. And there's a reason for this. Right? Because when we multiply two decimal numbers together, you can always move the decimal point to make sure that your numbers are between 1 and 10. And then when you multiply them, they're between 1 and 100. So we need to be able to go up to 100. So let's try using this very, very basic slide rule to multiply. We actually need 2 of these rulers side by side and mark the values 4 and 8. Let's line up the 1 of the bottom ruler with the 4 of the top one. Now the 8 on the bottom corresponds to 32 on the top. We have multiplied 4 by 8. Fantastic. Okay, that's all very good if we only want to multiply powers of 2. But what about other numbers? How can we handle that? I mean, we only have the powers of 2 here. Okay, we could just interpolate, linearly interpolate between these powers of 2 to have all the numbers from 1 to 100 at the bottom, like this. I'll just mention the numbers 10 to 100 just to make space. I missed off the final 0, so you have to interpret this 1 to 10 as 10 to 100. Let's try using this to multiply 6.5 and 5.5. Lining them up, we get about 32. Okay, it's not very close to 35.75, but it's not a million miles away, right? But that's to be expected. Right? We're interpolating between powers of 2. That's not going to be very accurate. Let's try again. But we want our marks to be closer together. And to do this, we can choose a base A closer to 1. So I'll take 1.1 instead of 2 this time. So we take powers of A until we get all the way up to 100. And now we have 49 equally spaced marks at the top of the ruler. And we have the corresponding powers of 2 at the bottom. And this is much better. These are much closer together. So if we linearly interpolate on the bottom of the ruler, then it's going to be much more accurate. Okay, one issue, right? As we've chosen A closer to 1, then our numbers at the top are bigger, right? We've got more marks, we have bigger numbers. To stop them getting too big, let's divide them by 10. So I'm moving the decimal point 1 place to the left. Okay, let's use this to multiply 6.5 by 5.5. We just line them up, and yeah, it looks pretty good. It's difficult to see exactly, but it's between 35 and 36. Okay, we can be even more accurate. Let's try a base of 1.01. We do this, now we have over 450 equally spaced marks at the top. So yeah, linearly interpolating between these is going to be pretty accurate, at least to the resolution here. And again, our numbers at the top are getting a bit big, so let's move the decimal point to the left 2 places this time. And we get something which looks pretty similar to the previous attempt. So let's use this slide rule to multiply 6.5 by 5.5. And doing this, we see, well, again, we get something between 35 and 36. So we're converged, basically. But look at this, right? If we look at the number 1 at the top of the slide rule, the number it corresponds to, well, it's e. And in fact, the numbers at the bottom are all e to the power of x of the numbers at the top. Or conversely, the numbers at the top are the natural logarithm of those at the bottom. And this is the same idea as in Napier's logarithms. He was using tables, So that allows more decimal places of accuracy than just looking at a slide rule. But the idea is the same. By choosing a base very close to 1, Napier was effectively compiling tables of logarithms to base e. Okay, there's plenty of other ways in which e and its associated exponentials and logarithms arise in a natural way. For one thing, there was what Jacob Bernoulli was doing, which he was trying to describe exponential growth coming from compound interest, which is actually when he first discovered the number e. But it also appears in plenty of other places. Exponential decay, say you have a radioactive compound. And improbability, E appears in the Poisson distribution, normal distribution, and unsurprisingly, exponential distributions. But let's move on. Now, the first step in giving a more modern analytic description of exponentiation is to note that its graph, or the shape of its graph, only actually depends on its behavior near 0. And this is because raising a base a to the power of x, this is the same as raising it to the power of x over n, and then raising the result to the integer power n. But if n is large, then x over n is close to 0. In fact, let's use a linear approximation to the curve near 0. So a to the x is approximately 1 plus a constant g times x. This means that a to the power of x over n is approximately 1 plus x over n times g, giving an approximation for a to the x of 1 plus x over n times g raised to the power of n. But does a good linear approximation near 0 like this really exist? Okay, well it does if the curve is differentiable there, in which case g is just its gradient at 0. Now it looks smooth, so differentiable, but how can we prove this? Well, this is where the magic of convexity comes to our aid. Let's look at the gradient of the line joining the points at x equals 0 and x equals some positive value h. Convexity tells us that this decreases to a limit as h decreases to 0. So a to the power of x has a right-hand derivative, as do all convex functions. But what about its left-hand derivative? Well, the gradient for step size h, this is a to the power of h minus 1 over h. We just extract out a factor of a to the power of h, and it gives the gradient for a step of minus h. So the left and right-hand gradients only differ by a scaling of a to the power of h, and this tends to 1 as h goes to 0. So the left and right-hand derivatives are the same. It's differentiable. In fact, if we look at the derivatives about a point x, any point x instead of 0, this scales in just the same way as a to the x does itself. Let's write out the derivative for step size h. And we extract out the factor a to the power of x to leave the gradient at 0. So we've shown that a to the power of x is differentiable everywhere, and its derivative is a constant multiple of a to the power of x itself. Now let's look at this equation. Let's circle it. Can we do better than just saying it's approximately equal? Yes, we can. Again, using the magic of convexity. We can do better than saying a to the power of x is approximately 1 plus x times g. By convexity, it is greater than this, giving a lower bound for a to the power of x. And we can also get a bound in the opposite direction. All we have to do is replace x by minus x, then take 1 over each side, which reverses the direction of the inequality. Okay, I'm assuming x is small here, small enough for 1 minus xg to be positive. But yeah, that will be the case. So to get the right-hand side in the same form as before, we can substitute x by x over 1 plus xg, rearrange a little bit, cancel some terms, and we get what we need. 1 plus x times g. And this is sandwiched between two exponentials. Now let's do the same as we did before for the circled equation. replace x by x over n and then raise to the power of n. And this is, well, it's really lovely, right? It's pretty good. The term 1 plus x over n times g raised to the power of n is sandwiched between these two exponentials. And the exponential on the right is just a to the power of x. And the exponential on the left, well, that's tends to a to the power of x as n goes to infinity by continuity. And our expression is sandwiched between them. So taking the limit gives this nice alternative expression for the exponential, just in terms of the gradient g. So now we have two expressions which involve this mysterious gradient g. But what is it? And how is the gradient related to the base a? Well, let's start by writing out the linear approximation about 0. And I'm using little o notation for a term which goes to 0 faster than x, so it's negligible for small x. And the gradient g, let's denote this by ln of a, so some function of a. And the notation will be clear in a moment. Now let's look at a to the power of y raised to the power of x. And this is just a to the power of x times y, so the linear term is going to be xy ln of a. This means its gradient in x is y times ln of a. And this just says that ln of a to the power of y is y multiplied by ln of a. But note, this has a pretty good implication. If we take any base a, not equal to 1, so a to the power of x is not constant, then ln of a can't be 0. So taking y equal to 1 over ln of a, this gives us a number e, where ln of e is 1. And this is what we want. This will be the base of the natural logarithm. To see this, let's just replace a by e in the previous identity. And it shows that ln is the inverse of e to the power of x. So indeed, it is the logarithm to base e. And in the top equation, we see that e to the x has gradient 1 at 0. In fact, looking at exponentiation in this way, it's much easier to just use base e. So all of the ln of a terms just go away. So let's do this. And let's also take our definition of a to the x and substitute in e to get our new definition here. And e is defined by this value close to 0 having gradient 1, so we just get this simple definition. The final statement here, that's just the same as saying that e to the x has gradient 1 at 0. Now, it's often much easier to work directly with e to the power of x rather than an arbitrary base, so it's even described by a special function, the exponential function. Exp of x is just the same thing as e to the power of x. Okay, that's fantastic, but what about the power series, I hear you say? I mean, some introductions to this subject just define the exponential function using the power series, and I haven't even mentioned it yet. Okay, but we can derive it. To do this, let's just expand out 1 plus x to the power of positive integer n. And the coefficients, they're just binomial coefficients. And let's write this with a summation notation. And let's put in the explicit form for binomial coefficients. And to get something like our expression for e to the x here, let's replace x by x over n. And we can reorganize terms a little bit. Exchange k factorial and n to the power of k, and then split this n to the power of k into individual n terms and absorb into each of the terms of the product in the binomial coefficient. Okay, this is good, right? The terms on the right, let's highlight them in blue. They're just the well-known terms in the power series. And their sum converges absolutely, since k factorial grows much faster than x to the power of k. And looking at the product, the terms, they're all between 0 and 1, and they tend to 1 as n gets large, so we can commute the limit with, as n goes to infinity, with a summation, to replace these terms by 1 as n goes to infinity. And this is allowed by standard properties of absolutely convergent sums, or if you like, by the dominated convergence theorem. Either way, we have the power series expansion of e to the power of x. Okay, we're now reaching the final step in our journey. That is exponentiation for complex exponents. But first, let's just check where we came from. Looking at the complex plane, we started by defining powers for integer exponents, shown in yellow here. Then we extended to rational exponents to fill in the gaps in blue. Then we took limits to extend to the whole real number line. But now we want to extend to the entire complex plane, this whole area here, most of which is not near the real line, so we can't just take limits again. But what can we do? Well, we can do something like we just described a moment ago. Suppose we take our definition and we just allow x to be complex, and then we look at e to the power of a complex number x. This should equal e to the power of x over n raised to the power of n. And as n becomes large, x over n is close to 0. So supposing the linear approximation there also works for complex x, this is approximated by 1 plus x over n. And the limit expression should hold for complex values of x as well. And you can prove this directly if you like, that this does converge and it satisfies the required properties. But we have several properties that we could work from, and any one of them can be used. And it's probably fastest to use the power series and show it satisfies our definition. So let's do this. Expand out the first two terms, and this gives exactly the linear approximation at 0. Okay, that was easy. But what about the other defining identity? E to the power of x plus y equals e to the x times e to the y. Okay, you could prove this by expanding out the series, the power series, and comparing coefficients for powers of x and y. And, well, this is an interesting exercise which I encourage you to try. I won't do that now. The fact is we already know that it holds for real exponents, so the coefficients must agree. And if the coefficients agree, then the identity also holds with complex exponents. So we're done. We know that there does exist a solution satisfying this definition, and it's given by the power series, and we've already shown this limit expression converges to the power series, so that also holds, as does the differential identity by differentiating term by term. Okay, so we've shown the existence of a solution to this definition, but there better be just one solution, otherwise it's not a good definition, right? I mean, it looks like there should only be one, but it needs proof. So how can we do this? We want to take something satisfying this definition and then show that it's equal to the e to the x, but we can use any of these properties for e to the x. I think the easiest one is the differential identity this time. So let's suppose we have any other solution to this definition, which I'll call x of x. So x of x plus y equals x of x times x of y, and it has derivative 1 as x is at 0. And then, as it has derivative 1 at 0, then using this defining property, its derivative at x is just x of x. So let's look at x of x multiplied by e to the minus x and differentiate it. Using the product formula, we can do this by differentiating each of the terms. And let's rearrange this. And there's some cancellation, and the derivative is 0. So using the simple fact that the only functions with 0 derivative are constant, then x of x is a constant multiple of e to the x. And comparing with x equals 0, this constant must be 1, so x of x equals e to the x. So there's a unique solution to the definition here. And this unique solution satisfies all the listed properties here. Okay, that's great. We have e to the power of x. But what about other bases? What about a general base a rather than e? Well, you could just say that a to the power of x is e to the power of x times the natural log of a. And in practice, this is often the most useful thing to do. But I'd like to have a standalone definition for the sake of completeness here. So let's try doing this. We allow x to be complex and we remove the continuity requirement. Instead, suppose that a to the x is differentiable as 0. We could always rescale the exponent to make this derivative 1. So a to the x is then going to be e to the x times a constant c. And just checking this at x equals 1, we see that a equals e to the power of c. And this is enough to infer that c is the natural log of a, just so long as c is real. There could be other solutions if it isn't. So all we need to do is add the property that the derivative at 0 exists and is real. And it follows that a to the x is e to the x times the natural log of a. Okay, so we've finished. We have now defined e to the x, a to the x for general complex exponents x. But what does it look like? What do these exponentials look like? Well, as any complex number, it splits into real and imaginary parts. So a complex exponent can be written as x plus iy. So the exponential is just the product of exponentials with real and imaginary exponents. And we already know what it looks like with real exponents, so only the imaginary case needs to be described. And looking at a to the power of iy, this takes us full circle back to Euler's famous identity. Let's look at e to the I pi again. This is e to the power of I pi over n raised to the nth power. And for large n, e to the I pi over n is approximated by 1 plus I pi over n multiplied by the natural log of e. But the importance of using e here is that its natural log is 1, so that term vanishes. And let's plot this approximation on the complex plane. As n increases, the powers of 1 plus I pi over n, well, they approximately wrap halfway round the unit circle. And generally, e to the it rotates around the unit circle at unit speed. So e to the I pi wraps halfway around the circle and coincides with -1. That's Euler's formula. We can say that it reflects the geometric interpretation of complex numbers as points on the Euclidean plane, or vectors from the origin to that number. And multiplication adds the angles that the numbers make with the real line. So exponentiation rotates at a constant rate. And I represents a unit vector orthogonal to the real line. So e to the it rotates at constant direction from the origin and at unit speed. I'll leave you to decide if that's beautiful, even the most beautiful formula in maths, but that's what it captures. Okay, that completes our journey through exponentiation, but there's some cool things I'd like to mention before I go. Exponentiation of complex numbers, that's just the start. In maths, we frequently take exponentials of matrices, or of linear operators, or tangent vector fields on a manifold, or Lie algebra elements. It's really a flexible and general idea. But let me point out one example. Consider functions f on the real number line, and define a shift operator s subscript y, which shifts the function distance y. Differentiating this with respect to y, well, that's the same as differentiating f, and I'll use d to denote the differential operator. Now let's remove the function f from this expression to get a pure operator identity. And this is just the differential form for an exponential. The derivative of s with respect to y is a multiple of s. So s is the exponential of y times d. Okay, at least it would be if d was just a complex number, but assume this still works where d is an operator. Then let's just plug in the series expansion for the exponential and apply to function f. Now if we just substitute back in the definitions of the operators on the left and in the sum on the right, the result is the Taylor series expansion of f. Okay, I swept a bunch of technicalities under the rug, but this can be made rigorous. The main point though is to illustrate how Taylor series are really an operator exponential in disguise. Now I'm going to leave you with one final exponential identity. Forget about e to the I pi. How about 45 to the power of 2? Or 45 times 45, which is 2025. That's right, 2025 is almost upon us and it's a perfect square. So have a perfect 2025 and I'll be back with more videos almost surely.